Now that we studied that there are now 12 possible water surface profiles that we have to analyze in gradually varied flow problems. So these 12 types of possible water surface profiles, remember, only for prismatic channels. These are for prismatic channels. If we have non-prismatic channels, then there are 20 typical water surface profiles can be shown that you can study if you are interested. Open channel hydraulic book by Venti Chow. So you can study in detail. But anyhow, we just stick to this prismatic channels, 20 possible water surface profiles. So before we try to analyze them, let us try to learn that how we develop an equation to tell us that the water level will be increasing or decreasing in the direction of flow. So for that, we first defined what is water surface profile, and then we will develop an equation for the gradually varied flow problems beside the energy equation that we studied earlier, and we will restrict our studies to rectangular channels. This is the next topic in your textbook. Now, as I said before, that we consider rectangular channels because for rectangular channel, the formulas are simple, and when we develop equation, it is easy to understand and develop. So that's why essentially we consider rectangular channels, but we can extend the discussion to non-rectangular channels. So first, let us know that what is water surface profile. So a gradually varied flow profile or gradually varied water surface profile is a line indicating the position of water surface. Clear? So what we mean by the profile of the water surface, that is actually the position of the water surface along the length of the channel. It is a plot of the flow depth as a function of distance along the flow direction. This is what we mean by water surface profile. The term water surface profile is used to generically refer to the shape of the water surface, how the depth changes with distance over a segment of stream reach. And these 12 types of water surface profiles we have to analyze. 12 types that we just discussed. 12 types are possible. For the given slopes, 5 slopes, and then the 3 types are zones or region. So 12 types of water surface profiles we will study for prismatic channels. Clear? Solution of gradually varied flow equation is a commonly encountered problem in open channel hydraulics, as it is used to determine, for example, how far upstream water levels might be increased and hence flooding enhanced due to downstream works such as installation of a bridge, dam, weir, etc. Hydraulic structures, dams, weirs, etc. Similarly, you construct a bridge. So we are interested to know that how far upstream the water level will increase. I already explained this in a slide. So that's why we encountered these type of problems in open channel hydraulics. That's why we need to study how to analyze them. Clear? So before we try to analyze them, we need to develop the gradually varied flow equation that is mentioned here. How we can develop this equation. So first let us try to develop this equation. Clear? Now we already write down that as we have this H, that is the total energy head, this is equal to Z plus Y, which is the depth of flow, plus we have the kinetic energy had alpha v square by 2g. So let's say this is equation 1. This is the total head at any section in open channel. Now what we do is that for the water surface profiles which are mentioned here, because the depth will vary in the direction of flow, so that's why we need to differentiate this with respect to x. So what we do is that we differentiate this equation 1, we differentiate this with respect to x, where x is the distance along the length of the channel with respect to x. This x is the horizontal distance along the channel. So the rate of dissipation of energy, because we are differentiating this, we already studied the energy decreases in the direction of flow. And with this alpha is equal to 1, as this is the assumption we made in chapter 8 pipe flow problems. Also we make this assumption in the open channel flow throughout this chapter. Alpha is equal to 1. When we differentiate this here, this equation 1 with respect to x, so what we will get is that this will be equal to dH divided by dx. This will be equal to dz divided by dx plus dy by dx. This will be equal to dy by dx, and plus we have 1 by 2g is common, alpha is equal to 1, and we have this d by dx into v square. Let's say this is equation number 2. Now in this equation number 2, you see that energy gradient that we defined S. So we have the slope of the energy line, this energy gradient. This is dH. H is the total energy. So energy gradient, this will be equal to S equal to dH by dx. This H is the total energy head. So the total energy that is with respect to x, this is actually your S. And because the energy is decreasing in the direction of x, we put a negative sign. And we already stated that this is equal to, okay, let me make it like this. This is exactly equal to L, not X. This is actually L. This is equal to L. But since in open channel we say that L is approximately equal to delta X, so that's why we can write down this as approximately equal to, this is approximately equal to minus dH divided by dx. This is approximately equal. We can make this assumption. So this is the S. Let's say this is equation number A. Then we know that the slope of the channel, so the slope of the channel that is denoted by S naught, that will be equal to dz by dx. We already write down this before, dx by dz by dx, and this is with negative sign. And slope of the hydraulic grade line, this is bed slope, slope of the channel bed, and slope of the hydraulic grade line, which is denoted by SW. So this SW will be equal to dz, this will be equal to dz divided by dx this is plus, but make it minus and minus both because it is also decreasing in the direction of flow. So dz by dx minus dy by dx minus dy by dx. So let's say this is equation number B, whatever you call, and let's say this is equation number C. Now if we put this equation A, B, C, okay, let me simplify this also here. This term which is written here in equation number 2, clear? Since we are dealing with rectangular channel, here we have rectangular channel, we can simplify this. So this term in this equation number 2, this can be written as, for example, 1 by 2g is common. So we have 1 by 2g, that is common, and this is equal to d by dx into v square. This is the term. Now we can express this in terms of the discharge. So this will be equal to 1 by 2g into this d by dx this will be equal to q square, small q, because rectangular channel, discharge per unit width, divided by y square and this can be written, if you differentiate this, take the derivative of this, so then this will be equal to minus q square. Now discharge is not changing. This is what we are saying, the steady flow. So discharge is not changing. So that's why this will be equal to minus q square by g. 2 will cancel out. This y2 square will go up, take the derivative, and this will be equal to 1 divided by y cube. And because it is other than x, so again we have dy by dx. You will get this term. This I have simplified this last term of equation number 2. So now when you put this equation A, B, C and this simplification in equation 2, clear? So this equation number 2 will become, this equation number 2, this will become minus S, this dH by dx, this will be equal to minus S from here, equation A, and this will be equal to minus S naught, this will be equal to minus S naught plus dy by dx so this is dy by dx into 1 minus q square divided by gy cube. Here this is y cube, so this will be q square divided by g into y cube. Now when you simplify this, you will get dy by dx. This is the rate of change of depth with respect to x. So this will be equal to S naught minus S. This S naught will go to the left side. So here we can write down S naught minus S divided by 1 minus Q square divided by G into Y cube. Now this here S naught minus S, S naught minus S, this can be written as 1 minus V square divided by GY. Now this here that I have write down here, that this dy by dx, which is equal to S naught minus S divided by 1 minus V square divided by GY. Now what is this equal? You see, we defined the Froude number. So Froude number is equal to V divided by square root of GY for rectangular channel, since we are talking about the rectangular channel. Now when you square both sides, so this will be equal to F square, that will be equal to V square divided by G into Y. So now it means that this will be equal to S naught minus S divided by 1 minus F square, where F is the Froude number. So this equation dy by dx, this equation dy by dx, this is equal to S naught minus S divided by 1 minus F, where F is the Froude number, F square. This equation is known as dynamic equation of gradually varied flow. This is in your book known as dynamic equation of gradually varied flow. Dynamic equation of gradually varied flow. Of gradually varied flow. Now in some books it is known as, a differential equation. It is known as differential equation of gradually varied flow. Equation of gradually varied flow. Now what is the use of this equation? This dy by dx is the rate of change of depth. So this equation actually tells us that the depth is increasing or decreasing in the direction of flow. This is very important, because if dy by dx, if you get the value, whatever value, now we are not interested in the value. If you calculate the numerator, you calculate the denominator, and you calculate the overall sign. If the overall sign is positive, then it means that water depth will be increasing along the channel. This would mean that water depth increasing. This is important. If you get plus sign, whatever the value, we are not discussing the values here. Water depth is increasing along the direction of, or you can say along the channel. Along the channel. And if this dy by dx, if this is negative, you get negative answer, then the water depth, that will be decreasing. That will be decreasing along the channel. So this is very important. Clear? When we solve the problems, we have 12 possible water surface profiles. This equation will tell us that the profile for any given condition, it is increasing or decreasing along the channel. So this equation, it represents the slope of water surface with respect to the bottom of the channel. This is important equation. It represents the slope of the water surface with respect to the bottom of the channel. Now, these we will discuss. I will explain also the numerator and the denominator. But let us, what we have studied so far, okay, let me explain here. You see that in case of the flows, you have to just qualitatively determine the sign here, and then qualitatively determine the sign of the denominator. We will arrive at the sign of dy by dx. Clear? So in this case, you see that this is the equation that we just developed. Dy by dx is s naught minus s divided by 1 minus f square, where f is the Froude number. If this is greater than 0, then it means that the water surface is increasing in the direction of flow along the channel. If dy by dx is negative, less than 0, it would mean that the water surface is decreasing in the direction of flow or along the channel. We will study different cases. We have already studied. For example, you see that when we have a drop, so in this case, the water surface, it is decreasing in the direction of flow. You can see here dy by dx is negative. So if this dy by dx is equal to 0, then essentially it means the water surface is parallel to the channel bottom. And that is the condition for uniform flow, because in uniform flow, dy by dx is 0. Depth is not changing with respect to x along the channel. And if we have horizontal channel, then dy by dx will be equal to s naught. It means that this surface will be again parallel to the bottom horizontal slope. So that's why this dy by dx will be actually equal to this s naught, because both will be parallel, clear, horizontal. And in case of critical flow, this dy by dx will be infinity. Why? Because for critical flow, Froude number is 1. This is for critical flow. So for critical flow, the Froude number is 1. So what will happen to the denominator? 1 minus 1, 0. Anything divided by 0 is infinity. So that's why this dy by dx, that will be infinity, means that the slope, it will be this one here, vertical. Clear? So this is how we should understand that this equation works. The signs of this equation will tell us about the nature of the water surface profile that can occur in gradually varied flow. 12 for prismatic channels that we discussed so far here. As we discuss here, 12 possible water surface profiles in case of gradually varied flow. We have to analyze individually. This is now the problem. Okay, Before we discuss, as I said, that depending upon the type of flow, this dy by dx may take the values dy by dx is equal to 0. When the depth is not changing with respect to x, you see the slope of the water surface here is equal to the bottom slope. The water surface is parallel to the channel bed, or the flow is uniform. When dy by dx is positive, plus whatever the value, remember in this case we are not discussing plus how much, no, just qualitatively we are discussing now, qualitatively. So the slope of the water surface is less than the bottom slope S0, that's why it is plus. Clear? You see here S is less than S0, that's why you get plus sign. It is possible. Okay, the water surface rises in the direction of flow, or the profile obtained is called the backwater curve, as I show you before for the dam. This we will discuss in detail also. So it means that the surface is increasing. For example, you have this dam, clear, and this is the water surface. It will increase because you store the water. So this is dy by dx is increasing plus. Clear? This is an example, and this resulting curve, this is known as the backwater curve. And also it is possible that dy by dx is negative. How much negative? No, just sign negative. It means that the slope of the water surface is greater than the bottom slope. The water surface falls in the direction of flow, or the profile obtained is called the drawdown curve. Just like as I explained, that let's say we have this drop structure, the water is flowing and then it will draw down and it will flow here. So this is known as a drawdown curve, decreasing in the direction of, this is let's say a drop structure as we already discussed, and this is the water which is coming here. So you see the depth is decreasing. So this is known as the drawdown curve. Now this is the equation that we just discussed. What you have to do is that, for example, in this case, I know that dy by dx is increasing. In this drawdown curve, I know because I saw the example earlier that it is a decreasing. But now for any other situation, how you know that dy by dx is increasing or decreasing? So what you have to do is that you have to qualitatively determine the signs of the numerator and the denominator, and then from there you have to determine the overall sign of dy by dx. Then you can say that for this problem, for this given condition, the water surface is increasing or the water surface is decreasing. So what you have to do is, let us take a few simplification to tell you how you calculate the sign here. So since we are considering rectangular channels for simplicity, let us make it more simple. We can apply this to non-rectangular channel, but you see that the equation becomes complicated. So that's why in all the time the analysis we consider the rectangular channel for understanding, easy to develop the equation. Now what we do here is that we further make it simple. Let us consider wide rectangular channel, because we just want to see how the equation works. Wide rectangular, wide and shallow. This we studied earlier, this assumption we make for simplification, wide and shallow channels. Of course, rectangular channel. Wide and shallow rectangular channel. We just want to simplify. Okay. Now in this case, we already know that V will be equal to small q, discharge per unit weight, divided by Y, clear, and we have this hydraulic radius that is equal to Y, the depth of flow. This is the assumption. So for this we can write down S. How you can easily calculate this S now for wide rectangular channel based on these. So this S will be equal to N into small q for wide rectangular channel, remember. This will be equal to 1.486, Manning's formula in BG units, 1.486, and we have Y 5 by 3, and this is whole square. And similarly, we have S naught that we can also write down in this fashion. In SI system, just drop this 1.48. This is in British gravitational system. This will be equal to NQ. N is the Manning's roughness coefficient. This will be equal to Y. You see the formula becomes easy. That's why we use this. So S naught, then this will be Y naught. Clear? This is S for the energy. This is S naught for the bed slope. So this becomes Y naught because with respect to S naught, we calculate this Y naught in the Manning's formula. So this is how we relate the two. Clear? Now in this case, this is also 5 by 3. From here, this is 5 by 3. 5 by 3. And just to be units consistent, so we write down 1.486. 1.486. And this whole square. Now you compare these two equations. When we compare these two equations, S and S naught that we just write down, if you compare these two equations, so what we get is that you will get S divided by S naught. You just from these two equations, this will be equal to Y naught divided by Y, and this will be power 10 by 3. This is what you get. So from here, what is the idea that you get? That the slope and the depth, they are inversely related. You can see here the slopes and the depths, they are inversely related for. So from here, what we see is that when Y is greater than Y naught, when Y, if you have the depth that is greater than the normal depth, what will happen is that S will be less than S naught. S will be less than S naught. See from this equation inversely, S will be less than S naught. And what will happen that this numerator, now we talk about the sign of numerator, how you will determine. So this S naught minus S, that will be actually positive. Just get the sign, that's it. This will be positive. And if we have Y that is less than Y naught, if we have this Y less than Y naught, then S will be greater than S naught, and S naught minus S, that will be negative. That will be negative. So this is how you can determine the sign for this numerator. Now come to the denominator. How you will determine in the problem the sign for the denominator. So we already know for this case that F is equal to 1. So this is corresponding to critical flow. This is we have critical flow. And if F is equal to 1, 1 minus 1 is 0, actually we are getting the condition that dy by dx will be infinity. Dy by dx will be infinity. So it means the slope will be vertical. Now, if F is greater than 1, if the Froude number is greater than 1 in the problem, then it means that we have supercritical flow. We have supercritical flow, and in supercritical flow y is less than yc. This is what we have learned so far. Y is less than yc. Then in that case, what will happen? This 1 minus f square, because f is greater than 1, so this will be negative. This is how you will determine the sign. And if f is less than 1, means we have subcritical flow. This is subcritical flow. In that case, y is greater than yc, and it means that 1 minus f square, because f is less than 1, this will be positive. You will get positive quantity. So this is how the numerator and the denominator signs you will determine. And this will determine the overall sign for dy by dx. These two signs together will give the sign of dy by dx. And for any problem, you will determine the sign for dy by dx, whether it is positive or negative. This is how we will solve the problems. Because this dy by dx, this is the slope of the water surface. Clear? So now in this case, before we try to apply this equation, we have this water surface profiles that are now given in your textbook. Now in this case, the basic equation that we just developed, this dy by dx, s naught minus s divided by 1 minus f square, this equation qualitatively we have to apply to determine that the water depth is increasing or decreasing in the direction of flow or along the channel for the 12 possible water surface profiles. How you know this? You will determine the overall sign of the numerator and the denominator, and then from there it will give us the resultant sign for dy by dx. If it is positive, the depth is increasing. If negative, the depth is decreasing along the channel. Now in this case, these are now the examples given for 5 slopes or channels that we discuss. For mild channel, this is your zone 1 or type 1 or region 1. This is your type 2 or region 2. This is your type 3 or region 3 or zone 3, whatever. So you see that 3 zones, the depth is possible in the 3 zones over the mild channel. So that's why accordingly we will write down that m. This is why I show you the letters that we discuss here. Now we are using them. Everything we are using them. Here you see S for steep, C for critical, M for mild, H for horizontal, A for adverse. So now to just make things easy, instead of writing these, we just use the first letters. So what we do is that now in this case we will use M. If it is any water surface level is in zone 1, type 1, region 1, we will say it is M1 profile. If it is in zone 2, type 2, we will say it is M2 profile. And if it is of type 3, as per our textbook, let us use type. If it is in the type 3, we will say M3 profile. Similarly, this will be the case for the other slopes. This is only for mild channels, where the slope is mild slope. S0 is less than SC. And these water surface profiles which occur, we have to analyze them. We just developed the theory for this. In these figures, we only determine that these profiles will be increasing or decreasing in the direction of flow. This is the direction of flow. So we qualitatively apply the dynamic or differential equation of gradually varied flow to get the net sign. And this is coming from the numerator and the denominator. We already know that this dy by dx, this is equal to S0 minus S divided by 1 minus F square. So S0 minus S. Now in case of M1 profile, if the depth is this solid black solid line, now y is greater than the 2. That's why we have type 1. Y is between the 2. That is why we have type 2. And y is below the 2. That's why we have type 3. Now to determine that this M1 will be increasing or decreasing, how you know? This M2 is increasing or decreasing along the channel, how we know? This M3 is increasing or decreasing along the channel, how we know? We get the idea from this dynamic equation of gradually varied flow. So we qualitatively determine that it will increase or decrease in the direction of flow. So let us consider only one example. You can do it yourself for the other. Let us consider this M1 profile. This is M1 profile. Mild slope, mild channel, and type 1, M1. So in this case, we have S0 minus S. What is the situation that the depth, here we just discussed, when your depth is greater than Y0. Here, this one here, we just discussed. Our depth is greater than Y0. S will be less than S0 and this will be positive. So you can see here that depth is greater than Y0. So that's why S will be less than S0. So that's why we get plus. Whatever is the value, it will be plus. We are not interested in the numerical value. Now that Y is greater than YC, what we studied for the denominator, Y is greater than YC here. This is subcritical flow. F will be less than F1. F will be less than 1. So 1 minus F square will be positive. So it means that Y is greater than YC, F will be less than 1. So it means it will make this quantity as positive. So now we already know that positive divided by positive is positive. So it means that M1 profile, this is increasing in the direction of flow. And these are the typical examples which are given in your textbook where this profile can be encountered. This is not the only example. There can be other examples where we can find M1 profile, but this is just for understanding purposes. One example is given with all the profiles, the 12 profiles that are possible. Now for M2 profile, you can see that y naught is greater than y. So consequently, S will be greater than S naught. That's why the numerator is negative. But y is greater than yc. It means f will be less than 1. That's why the denominator is plus. So minus divided by plus, that will give us the negative quantity. So it means that M2 will be a decreasing profile along the channel. And similarly, you can do it for all the other cases. These are the typical examples where M2 profile can be encountered. Now M3 profile, you have mild slope, but the depth is less than YC. It means that in this case, we have supercritical depth on a subcritical slope, because we are forcing the flow to come to the supercritical depth. This is supercritical depth. Normally, supercritical depth should not occur on a mild slope. It should occur on a steep slope. Because we are forcing the water to flow at this depth due to operation of this gate. So we have a supercritical depth on a mild slope. So M3, the resultant is minus divided by minus, still we have plus. So it means M3 is a rising profile. It will be increasing along the direction of channel flow. So this is the three profile, existing possible three profile, along with example for mild channels. We have 5 types of channels. So now you can understand from this equation for the other types. When we have the steep channels, then this is the situation. For S1 means that steep channel type 1, you get plus. It means that the slope, the channel water surface is increasing along the direction of the channel. See here S1. Now the channel slope is steep. We have steep slope channel. So S1 will be increasing in the direction of flow. Now when you calculate S2, the type 2 profile, this is negative. It means that S2 is decreasing in the direction of flow. Similarly, S3 is plus. So you can see that S3 is increasing in the direction of flow. And they will meet this normal depth line. This is Y naught, the normal depth line, asymptotically. They will appear to meet it asymptotically. Because if this line exactly meets here, then it will be a uniform flow. You have Y naught, then it will be a uniform flow. So that's why for this to remain gradually varied flow, it should meet asymptotically. But this is how you can determine qualitatively the science, and you can determine that S1 profile will be increasing in the direction of flow, S2 will be decreasing in the direction of flow. This is an example. And S3 again increasing in the direction of flow. So these are, you see, the possible, they with typical examples given. Now let us come to the critical channels. So in case of critical channels here, you see only 2 profiles possible, because Y naught is equal to YC. So the depth cannot be between the two, because Y naught is equal to YC. So that's why C2 profile is not possible. It is not possible. So either we have C1 profile or we have C3 profile. So we have the critical slope. So it means 2 slopes, 2 profiles are possible on critical slope. Of course, we should not design the channel for critical flow to occur, because it is unstable. But it can occur. You see, these are the examples that we can establish the critical flow to occur. This is for understanding purposes, but we already learned that we should not design the channel for critical flows because this is unstable. Now, if I come to the horizontal slope, horizontal channels, then you see that y naught is infinity, undefined. The depth cannot be infinity. See, this is theoretical result. So this y naught, it is infinity. So it means that the depth cannot be above infinity. How it is possible? So that's why the depth can be between the two. So we have h2, and below the 2, that's why we have h3. So it means that h1 profile is not possible. This is not possible. Only we can have h2 and h3 profile on a horizontal slope. And remember, this horizontal slope and adverse slope, they should be of smaller length, because if they are of greater length, we cannot establish the flow. So H2 is a decreasing profile, negative, and H3, if it occurs, it will be an increasing water surface profile, and these are the typical examples. Similarly, for adverse slope, the fifth one, again A1 is not possible because this is not possible. Profile A1 is not possible because it cannot sustain the normal depth. So H2 is a decreasing one, and A2 is a decreasing one, and A3 is increasing one as the sign determined by this equation. So this will tell us qualitatively the profiles are increasing or decreasing. Then how to establish or how to draw these profiles? This is another problem. This is another problem. We will apply a method, how you establish, how you draw these profiles. This is another method. At the moment, we are only studying that these are increasing or decreasing. So you can see that from this figure, you see that one way is use this equation to determine the net sign, and that can tell us increasing or decreasing profiles. But later on, you will learn when you become expert that all the type 1 and type 3, they are plus, all. They are always increasing. And all the type 2, they are decreasing. When you become expert, you will no need to apply this equation to determine the sign. They are plus, all. They are always increasing. And all the type 2, they are decreasing. When you become expert, you will no need to apply this equation to determine the sign. Okay, before I wind up this discussion, there are one or two things I want to explain. What are two, three things are, you see that I even discussed it before, that when we draw these profiles, so these profiles, when you draw the depth range, for example, the depth range is from here to here. These should not cross the critical depth. This is the critical depth here. Similarly, if you draw the M2 profile, the M2 profile should not cross the critical depth. That's why it is shown dash dash here in your book. And the reason is that we already developed the equation. You see, you have this equation here. And if you use the Manning's formula, so then in that case, what will happen is that in this Manning's formula, if you put the values, you use the Manning's formula, we have this Manning's formula. So this equation, then we can simplify to this equation here. Dy by dx, and this will be equal to S naught into 1 minus y naught by y, and this is whole power 10 by 3 This is whole power 10 by 3 divided by 1 minus yc divided by y. This is whole power cube. Now in this equation, you see that when y is equal to yc here at this point, when y is equal to yc at this point, so yc divided by yc, it will become 1. And 1 minus 1 is 0, and anything divided by 0 is infinity. So what I am saying is that when y is equal to yc, now this equation then gives dy by dx. This equation gives dy by dx is equal to infinity. So that's why it means that the slope here should be vertical. So that's why it is not possible that the slope here will be vertical at the critical depth line here. That's why the gradually varied flow formulas that we develop will not work here. And I already explained this in this lecture before the break. So that's why we cannot draw a solid line here. This depth should not cross the critical depth. When y is equal to y naught, you see here when y is equal to y naught, now y is equal to y naught in the numerator. So y naught divided by y naught is 1. 1 minus 1 is 0. Anything divided by 0 is 0. So what will happen is that this will give us dy by dx, dy by dx is equal to 0. That's why you see here that the profile will meet the normal depth line asymptotically. It will meet the normal depth line asymptotically. Now in this case, when y is equal to 0, when you have y equal to 0, when y is equal to 0, what will happen? Y is equal to 0. Anything divided by 0 is infinity. Anything divided by 0 is infinity. So we have what? We have this dy by dx. This is dy by dx. This will be equal to infinity by infinity form. This is what we get. Infinity by infinity from this equation when y is equal to 0. So this is undefined. That's why near the bottom of the channel again we have a dash line. We cannot show it a straight line because Manning's formula, this equation coming from the Manning's formula, it gives us the form infinity by infinity. So that's why you see here that the gradually varied flow theory will not work here. That's why we cannot plot a profile here and it is shown dash dash. You can see here it is shown dash dash here. Cannot be a straight line here. Clear? So these are a few things that you should understand from this theory here. Now the thing is that how we plot these profiles, how you can plot S1 profile, S2 profile, S3 profile, and so on. These 12 types of profiles that we just studied, how you can plot them. For this we have different methods. Only one method that is explained in your textbook that we will follow, but you can study the other methods also. So that's why the next thing is, before we discuss that, examples of water surface profiles which are given in your textbook, the M1 curve, I already explained this, that you have this normal flow in the channel. This is the original water surface. But when we construct a hydraulic structure, the water level will increase and the effect will travel upstream, and this will result in M1 profile. And this is known as the backwater curve, the famous backwater curve, because dams where these we construct frequently. So this backwater curve in natural stream. So this is an M1 profile that we just discussed. These are examples you can encounter clear practically. These are given in your textbook. Similarly, other examples are explained for subcritical flow, that we have a mild slope, and if it meets a milder slope, what will happen is that the water level will increase at the break in the slope. Here the water level will increase. This will result in M1 profile, and after the break the water will flow with uniform flow condition. If we have a milder slope channel meets a less milder slope, then in that case we will observe a decrease in the water surface, and this will result into M2 profile. You can do the analysis. These are given in your textbook. Now another example which is given again with reference to subcritical flow. If we have a wider than downstream channel, now here the channel width is wider. For example, you have this channel and then it meets this channel. It meets this channel. This is wider and this is less. So wider than the downstream, and the downstream is narrower than the upstream. So the behavior of water is that at the break, change in the width now, the slope is the same. So we will observe an M1 profile, that the water surface will increase. Similarly, if we have a narrower channel and it meets a wider channel, now we have narrow channel and it meets a wider channel. Let's say this is a wider channel. So then you will see that the water surface will decrease and we will observe an M2 profile. These are the different examples that we can encounter in open channel hydraulics. And similarly, you can observe this behavior for supercritical flows. These are the example given in your textbook for subcritical. This is again for subcritical. You can follow the similar and analyze for supercritical flow conditions. So we encounter these gradually varied flow situation. That's why we study this gradually varied flows. Now I will just explain the method. We will solve the problem in the next class. Now the final question remains is how to compute the water surface profiles. How you will compute them. For this we have different methods. For example, we have the graphical integration method. We have the method of direct integration. We have the direct step method. We have the standard step method, different methods. If you want to study them in detail, study the book Open Channel Hydraulics by Wen-Ti Chow. Only one of the method we will study in this course due to limitation of time, but I will give you the idea about one more method. So our main focus will be the direct step method. This is known as the direct step method in sub books. In your book, in our textbook, it is written step-by-step method, stepwise method. So this is also known as the direct step method. Why direct step method? Because no trial and error procedure. We get the direct solution, so that's why direct step method. And this method, it answers that if two depths are given, how far apart they are. For example, you have channel and let's say we have 4 feet of depth here, and you have 3 feet of depth here. Just an example, this will be the water. So what is this delta X? This is what we find in this method. How far apart? What is this delta X? Given two depths, how far apart? So we have already developed the theory for this. Now let us see that how step by step we proceed, and we will solve the problem for computation of water surface profiles using this method. So this method, it considers the difference in specific energy because the depth is changing at two locations. So that's why we have non-uniform flow, and relative to channel slope and energy grade line slope at midpoint between the two sections. Why? Because we go for the average conditions. This is what we write down earlier. You remember V bar, Rx, RH bar. We remember, so it means we are averaging conditions at the two sections. Let's say this is section 1 and this is section 2. So now the depth is not the same. So consequently, the velocity will not be the same. Consequently, the hydraulic radius will not be the same. So what we do is that in this delta X, if you remember, we developed the equation for this. And in that, when you calculate the slope that we encountered using the Manning's equation, the average conditions. If I go back, in here, this is the equation that we developed. And in this equation, we stated that this S, it is how it is calculated. For the average conditions, V bar and RH bar, and V bar is V1 plus V2 by 2, and RH bar, hydraulic radius, is RH1 plus RH2 by 2 for the two sections. So that's why we come here, and in this equation here, we say that midpoint between the two sections, because we are averaging the conditions. So what is this? Let me just quickly explain the steps, then I will stop the lecture here. So in this case, first we divide the depth range of interest into small increments, usually equal. We will divide them into equal increments. As I said here, the depth range will be given, let's say 3, and this is 4. We will divide this into equal increments. Delta X1, delta X2, delta X3, delta X4. So this we will divide. Then what we will do is that these small increments define the reaches whose lengths can be found by this equation. We already discussed this equation. You can determine delta X using this equation, and in this equation, S will be given by this equation that we just discussed in British gravitational units and in SI units. So S will come from here for average conditions, V bar and RH bar. Then this discretization process must begin from a section where Y is known. That is from calculations for a control section or from a field measurement at any section. For example, we have a dam, a weir. So we already know the depth we can calculate. So what we have is that, let's say this is the procedure. Let me extend this further. Okay, this depth we already know over here. We already discussed, for example, the weir. This water will flow over this weir control section. So we already know the depth at the control section. And then you proceed downstream. That what is the depth here? So essentially what we are doing is that, let's say, just I explain, let's say for example we have 4 feet, and then the downstream the depth is, let's say, 3 feet. So what we will do is that this profile will form. We will divide this into different sections. How many sections? The smaller the section, the greater will be the accuracy of the results. Because we are applying the Manning formula, so the smaller the section, the greater will be the difference between the depth and accurate will be the results. Because for Manning formula, we are assuming it to be uniform flow, which is not the case. That's why we have approximate results. Our result is not 100% accurate. So we divide this into delta x and this as delta x1, and then delta x2, delta x3, delta x4 up to delta xn. And then this delta x will be summation of all the delta x's from I is equal to 1 to n. All the delta x that you will consider I. That will give us the total distance for between these two consider. And the depth here you will consider. For example, let's say this depth is 3.9 feet. So I want to find out that how much upstream of 4 is 3.9 feet. How much upstream of 3.9 is the distance 3.8 feet depth. And so on till we reach to 3. So it says that this discretization process must begin from y is known, because you need a control point. If depth is unknown, then how we can proceed? In this equation, if depth is also unknown, how you can find delta x? If we do not have control section, you can go to the field and measure it by any method that you learn. How to measure the depth of flow. If the resulting value is negative, means that you calculate delta x and it is negative, because we calculate this distance cannot be negative. But when we solve the problem, you will see that this delta x may be equal to minus 100 feet. This can come the answer. So it does not mean it is incorrect. If the resulting value is negative, this means that the section 2 is upstream. This would mean that, like for example, for 4, now 3 is upstream. So when you calculate delta x, it will be negative. So you will write down that 3 feet is upstream of 4. And if it is positive, if we have plus 100 feet answer, then it means that section 2 is downstream of this. Then in that case, 3 will be here and it will be like this. So that's why delta x can have plus minus sign. It doesn't mean that it is incorrect. It would only mean that the section is upstream or downstream. From that point you consider. So we will solve a problem on this in the next class. Then you will understand how we apply. And another thing is that this method, direct step method, it is only applicable to prismatic channels. I will explain that when we have non-prismatic channel, we have another method for that. That is known as the standard step method. But that is essentially a trial and error procedure. So difficult than this one. That is known as standard step method. This is direct step. So no trial and error. We get the solution direct. That is known as the standard step method. And this standard step method, that is applicable to prismatic as well as non-prismatic channels, natural streams and rivers. And this is the method that is implemented in a HACROS. If you study the HACROS, if you have worked Hydrologic Engineering Center river analysis system, that we analyze the river flows, that is known as HACROS, river analysis system. They have implemented this method, because this can be applied to natural streams as well as prismatic channels. So, but this we will not study in detail, because this is essentially a trial and error procedure, complex. So that's why our main focus will be on this method. But I will explain in this method how we proceed to solve the problems. So this is computation of water surface profiles. There are many methods. We will just focus on the direct step method, and I will give you introduction on this standard step method, how we compute the water surface profiles for gradually varied flow. So in the next class, we will solve these problems that will help us to understand more